welcome back. So as you can see, we start with a NOT logic gate. This is a symbol for the NOT logic gate where input is variable A, output is a variable Y. Here is a truth table where for A equal to 0, output is complemented, and when A is 1, output is again complemented. That is, for 0, output is 1. For A equal to 1, output is 0. This is a Boolean logic equation which says output is complement of the input. Now, this is a schematic of a multiplexer where we see there are two data inputs I0 and I1, one single output Y, and one select input S. This is a truth table that we will see how we are implementing a logic NOT gate using 2:1 MUX. The logic equation for the 2:1 MUX is given as I0 and S bar or I1 and S, that is equal to output Y. So output Y is true when this term is true or this term is true. So when S is equal to 0, we know that I0 is getting connected to the output Y, whether logic 0 or logic 1 is present at I0. When S is equal to 1, we know that I1 gets connected to the output, whether I1 carries 0 or logic 1. So first condition here in the truth table we see when S is equal to 0, output gets connected or input I0 gets connected to Y, and S is equal to 1, input I1 gets connected to the Y. So we have to put the value of I0 and I1 in such a way that so that this select input maps the input here with the logic NOT gate. So when S is equal to 0, it is similar to when A is equal to 0. We want output to be Y. So output Y should carry I0 and I0 should be set equal to 1. So we'll see here now, we set here S is equal to 0 and we have set I0 is equal to 1. Therefore, Y is equal to 1 because with S equal to 0, we know that I0 gets connected to output Y. Now, next case, we see that S is equal to 1. So in this case, when S is equal to 1, Y is connected to I1. So I1 value should be set in such a way that this complements the input. So what we do here, I1 carrying a logic 0, that's why here comes logic 0. So this is similar to when A equal to 1, output is equal to 0. So this is how we can see that 2:1 MUX is used to implement logic NOT function. Let us move to the next logic. Let's say I have a logic of buffer. So in this case, this is a logic equation for the buffer, which is output is uncomplemented form of input. So or simply output is equal to input. Input is A, output is Y. Here is the truth table. When input A is 0, output is 0. When input A is 1, output is 1. Now the task is to implement this logic of buffer using again same 2:1 MUX. So for that, here is again comes a logic diagram of 2:1 MUX, which is similar to this structure. However, we have to implement the function of 2:1 in such a way that it will behave as a buffer. So again, let us now write the condition for S is equal to 0. When S is equal to 0, as per this truth table, we know that I0 gets connected to the output Y. And when S is equal to 1, we know that I1 gets connected to the Y. So how do I select that? When S is equal to 0, it is similar to when A is equal to 0, output is Y equal to 0. So we want Y to be 0. So I set I naught is equal to 0. That's how for S equal to 0, I naught gets connected to Y. However, now I want when S is equal to 1, the I1 should be set equal to 1 so that with this control, let me write here properly. When S is equal to logic 1, I set I naught is equal to 1 so that I1 gets connected to output and Y equal to 1. So this is basically mimicking or behaving the logic function of a buffer. So now let us talk about AND logic. This is a two input AND gate. A and B are the inputs, output is Y. This is the logic equation, Y equals to A and B, and this is a familiar truth table. So output of AND gate Y is equal to 1 only when both of its input are logic 1. So now we want to use 2 is to 1 mux or 4 is to 1 mux to implement this function. So let me show you how we can do that. So what we can do here is we'll use 4 is to 1 mux, as you can see that. And for 4 is to 1 mux, I have got 4 input data lines, one single output line, and two select lines S1 and S0. Remember, S0 is the least significant bit. Okay, now here is a Boolean equation for 4 is to 1 mux. So where we see that output is true if any of this product term is true. Here is a truth table where we see that output is Z here, but we have seen Y here. So let us say this is called as Z. Okay. So what we see here is when S1 and S0 are 0, output gets connected to the I naught. And when S1, S0 are 0, 1, I1 gets connected to Z. When S1, S0 are 1, 0, I2 gets connected to output. And when S1, S0 are both 1, I3 gets connected to the output. So this is the familiar truth table. Now we have to make sure that this multiplexer 4 is to 1 mux will behave as logic AND gate. So how we do that? So we know that here the inputs are A and B, and here the inputs are S0 and S1. So let us call it as this call, we call it as A. Let me write over here. This is A and this is B, which are the two inputs of the AND gate. So when I say S1, S0 are 0, 0, I know that I0 gets connected to the output C. So when S1, S0 are 0, 0, output is 0 here for the AND gate. So I will put I naught is equal to 0 because that is how I want for S1, S0, both 0. I know that I0 gets connected to the output Z here or Y here. This is actually output C. Okay, now for the second condition, when S1 at 0, 0, 1, which is similar to reading when A and B are 0, 1, because we see that we have mapped these two. So for that, I know that I1 gets connected to the output. So I1 value here should be 0. So basically, I would say it is 0. So you see that this is I0, this is I1, this is I2, and this is I3. These are the values of the variables. So I2 has to be 0 and I3 has to be 1. So final conditions 1, 1, I3 gets connected to the output, and therefore I know that I3 is set to be 1. So based on the select line inputs right over in this truth table, you can see that I am implementing the logic AND function y equals A and B. So here similarly Z, output Z of the multiplexer are receiving the 4 input data lines, and that is basically a AND function. Let us move and understand how we can implement logic OR gate. So this is again very similar. True input AND gate. Logic equation is y equal to a or b. This is OR gate actually. Logic gate is a or b. This is the truth table of the logic OR gate, where we know that output of logic OR gate is equal to 1 when any one of the input is 1 or both of them are 1. For when both of them are 0, output is 0. So again, we need to use multiplexer that can use and implement this function. So for that, you see here, again, it is very similar to this case. This is the same multiplexer that we have used with 2 select lines, 4 data lines. Output is Z actually. So output is Z, and this is a familiar truth table. We know that based on the select line inputs, which input get connected to the output here. So what I am going to treat here or do here is that this is input A, this is input B, which are basically mapping or map to the select lines. So when I am saying S1, S0 are any one of these four possible combinations, I am saying A and B at the OR gate. And accordingly, I have to set the values of I0, I1, I2, and I3. So I can see clearly I0 here is set to be 0, I1 is set to be 1, I2 is set to be 1, and I3 is set to be 1. And then when I select any one of these input combinations, output C here gets the value of any one of them based on the select input combination. And this is the way this multiplexer is behaving like a logic OR of the two input OR gate. So this is how we see that we have implemented successfully the OR logic. Now it's time to move for the next logic gates. So this is a logic NAND gate. Again, two input logic NAND gate. Output is Y. The function of the NAND gate is Y equals to A and B bar. So let me write here a bar. When we do that, this is a truth table of the logic NAND, which says the output of the logic NAND is 0 only when both of its inputs A and B are 0. For other possible combinations, the output is logic 1. So we have to use the multiplexer that will allow us to implement this logic. So how do we do that? Again, the same 4:1 multiplexer comes here, and the job of a designer is to set the values for I0, I1, I2, and I3. So we clearly see that I3 is set to be 0. For I2, to I0 and I1, they are all set to be 1. And now based on the select line inputs A and B, basically I will implement this truth table. So for all four possible combination of S1 and 0, I am basically getting this four possible combinations of A and B for the logic 1. So you see here, when both S1 and S0 are set to 1, I3 gets connected to the output Y, and I3 carries the value of 0. For other possible combination of S1 and 0, which are basically A and B, according to this truth table, I0, I1, or I2, one by one gets connected to the output. Finally, I implement a logic NAND here. Now let us move to very similar example to implement logic NOR function. So how do we do that? This is the logic NOR function. Again, I have to put the bar here. So Y equals A NOR B, and NOR is a complement of OR, which says output of a logic NOR is equal to 1 only when both of its input A and B are logic 0. So again, to implement this, we need 4:1 MUX. I have to set the values of I naught, I1, I2, and I3 in such a way that when the multiplexer function z is implemented, I will have one by one them connected to the output. So I0 here is logic 1, I1 is 0, I2 is 0, and I3 is 0. This is how, based on A and B or S1 as 0, when I select any one of these combinations, one by one, the output gets connected to the input, or in other words, vice versa. And I will have the implementation function y equals A nor B. So this is how we have successfully implemented NAND logic and the NOR logic. Now, you see at how we can implement two input XOR logic, or even we can implement an input XOR logic. So here is the logic symbol of XOR, exclusive OR. In simplified form, output Y is said to be exclusive OR of A and B, two inputs. So in simplified form, we say A and B bar, or A bar and B, that is equal to Y. So this logic function tells us the output of this logic is 1 if any one of the input is logic 1. For other possible combinations, output is always 0. So how do we do that? Again, we have to use 4 is to 1 MUX. So you can now clearly understand, and very simplified form, these are the values of all the four inputs that one needs to set. This becomes I naught, this is I1, this is I2, and this is I3. So here we see that value of I naught is 0, I1 is 1, I2 is 1, and I3 is 0. So that when S1 and S0 are both selected in this four possible combination, either I naught through I3 gets connected to the output Z. And finally, this output is basically implementing or behaving the logic exclusive OR function, because they are getting one by one connected to the output. So this is how we've seen how we implemented two exclusive OR logic using multiplexer. Now, finally, this is exclusive NOR, which is a complementary form of exclusive OR. So here, logic equation says y equals to A exclusive NOR B, or simplified form is A and B, or A bar and B bar equals to y. So truth table says the output of the exclusive NOR is logic 0 when or if any one of them is logic 1. If any one of the input is logic 1. Otherwise, the output is 1 if both inputs are same, either 0, 0 or 0, 1. So it's very straightforward. We again use our 4 is to 1 MUX, where we can clearly see I naught to I3 are four data inputs. We have to set the values of I naught and I3 up to I3 according to this logic function. So this is I0, I1, I2, and I3. So here I naught is logic 1, I1 is 0, I2 is 0, and I3 is logic 1. And here S1 and S0 are the two select lines, which are basically, or in other form, we see they are input of two input exclusive NOR gate. This is output Z of the multiplexer. Here is a truth table based on if any one of the four possible combination we select for S1 and S0, the output gets connected to the input, or input line gets connected to the output. So select the values of S1 and S0. So this is how we have successfully seen how we can also implement logic XNOR using 4 is to 1 MUX. Maybe the task for you here is to show how you can use 2:1 MUX to implement two input logic gates such as AND, OR, NAND, NOR, XOR, and XNOR. So hope you found this module useful. If you do so, share it with others for wider reach and stay tuned for more engaging content like this. Till then, we wish you happy learning.